uh, it's give like this. So basically it starts from x dot t, okay? From this x dot t, you do the integral respect to time, and then you get xt. And then, so this mean this signal from here mean at times x, right? If you remember from the previous lectures on block diagram, how to do some manipulation on the block diagram. So this is a junction. The signal come here is positive. The signal come to this direction is also positive. So x dot t just equal to at times this x plus bt times u. Okay, you got x dot t, which is the first equation, and also yt, which is equal to this direction, positive direction. So ct times xt plus from this direction dt times ut. Okay. Okay. Let's move to the next section, which is forming a state space model. In this section, you will learn how to form a state space model. So uh, from the previous lectures, you learn how to model mechanical system, you learn how to model uh, electrical system. Okay, now it's time to take advantages of those techniques and learn how to form state space model. In order to form the state space model, first you need to have the equations of motions. Okay, you can get the equation of motion from Newton's second law of motion or Lagrangian. And after that, you need to choose the state variable. So the variable that so the state variables are the variable that determine the behavior of the system. For example, if you consider the cart moving along horizontal direction, its position, its placement or position, and velocity are enough to determine the behavior of the system. And then you take the derivative of the state vectors, then write the state space form, and finally write the output equations. Okay. So consider this simple example. Okay. So we try to derive the state space model. I mean, not try, but we would like to have the state space representation of this system. Okay. So this is a differential equations, y dot dot plus 4y dot plus 3y plus 2u. And the first step is given. You have the equations of motions, the dynamic system already, and then we need to choose the state variable. So I will choose y, the displacement, and its velocity. So x1 equal y and x2 equal y dot. Then this is the state vector, x equal x1 and x2, basically y and y dot. And step number 3 is to take the derivative of the state vectors. So we have, this is x, maybe you take the derivative with respect to time, you have x dot 1 and x dot 2. So x dot 1 is just this one dot, right? Will be y dot. So this is y dot here, and x dot 2 is this one, y dot, and then you do the derivative one more respect to time, you will have y dot dots. And you can have the y dot dot from this equation by throwing this term to the right hand side. Okay, so 2u minus 4y dot minus 3y. And step number 4 is to write the state space form. Okay, you have this one. Then from this one, you just need to replace the variable using x1 and x2. So y dot is just x2, and then y dot here x2 as well, and y is just x1. Replace this and then write in matrix form, okay, like this. So basically, if you multiply this with this, you will have x2, and if you multiply this with this, you will obtain this 2, this one, and the final term is this 2u right here. Okay, so this is ax plus bu. So this is matrix B, this is matrix A, and then write the output equations. So y can be chosen as y equals cx, so 1, 0, and then x, x1, x2. In this case, we are only interested in the displacement. So if you if you are interested in the velocity as well, you can put 1 and 1 here. Basically mean that for the physical system, it means that you can measure the position and the velocity. Okay. Move to the next example. The next example is mass spring damper. Okay. So now we want to find the state space representation for the system shown below, and the output is the displacement of the mass. Okay, so we have the mass here, and this is a displacement y. So dy dt is the velocity, and you have an input force F. Okay, point from this direction, in this direction, and then this mass is attached to the wall by the spring and the damper. So C dy dt are the force that is created by the damper in the opposite direction, and this is the force created by the spring, Ky. Okay, and this is the equation of motion. Okay, from Newton's second law, ma F equal ma. So m, a is the acceleration. Acceleration is y dot dot. And then you have this force. I should write this the capital F, but sorry for that. This one is this one. And then yeah, minus at minus ky, because this force has the opposite direction, and also this force has the opposite directions. Okay. And step number 2 is to define the state variable. So you choose x1 and x2. This is exactly the same as the previous example. Okay, but that one was only the differential equation. I simply show you the differential equation, but this you have the parameter, for example, mass and force, K and C. And then take the derivative. So if you take the derivative of x1 dot x1 and x2, you will have y1 dot, and y1 dot is just x2 here, and y dot dots can be obtained from this. Okay, you need to take this m to this side. So f over m minus km x1 minus cm x2, and from that you have to write in matrix form. Okay, just put this, and then if you multiply this row by this column, you will have x2. If you multiply this row by this column, you will obtain this. Okay, and this is the input or on this side. So you have ax plus bu, and then last equation is the output equation, y equals cx plus du. In this case, we assume that there is no we assume that d equal to 0. So 0, 1. If the output is a displacement, this should be 1 and then 0 here. Okay, sorry for that. So 1 and 0.